You've got to check this little Twitch dashboard. It's actually pretty cool. Tweet it out. Are we connected? We're on? I think we're on. If you're joining the chat, please let me know. I might put it in Discord as well. Why not? Discord. I've got so many tabs open. Standard working on a new project. Or a semi-new project. I'm going to put it in machine learning, data science. And mixed precision training. Boom. Boom. Ashik, what's up, my brother? How are you, my friend? I've been going through full stack deep learning, by the way. If you're joining the stream, please say hi. And please let me know if you can hear me and you can see me and you can know what's going on. So this is a stream. Today's date, it's the 4th of March. March 4th, baby. So yesterday we worked out, or we beat the deep food paper in about 20 minutes. So that was pretty cool. And we learned that mixed precision training gives us a speed up, a massive speed up in the case of EfficientNet B0, gives us a speed up of about 3 or almost 3x, so 2.5x. So what I figured today, let's get rid of some tabs. This is a great course, by the way, Full Stack Deep Learning. Go check that out on YouTube. You'll see me commenting here. Where's my comment? Sort by newest first. Why isn't my comment there? I commented a bunch of cool things. Can I show other people's YouTube videos on stream? It's not showing my comment. Anyway, doesn't matter. Today, let's figure out what we should do. What should we do today? I'm going to close a bunch of tabs. Oh my goodness, look at this. Close that. TensorFlow datasets. We got familiar with TensorFlow datasets yesterday too. And training a neural network with MNest and Keras. I need to get rid of some whole windows, actually. I've got some great notes on the Full Stack Deep Learning course. We'll get at that. That's not what we're doing today. We're doing some more mixed precision. I want to actually make an example of mixed precision, so I really get it down pat. So TensorFlow datasets. I think all I want is these two windows. So let's get this one. We'll get it out of that, and we'll get into that, and boom. Speeding up models in TensorFlow with mixed precision. Let's do that. Speeding up model training in TensorFlow with mixed precision. Okay, this will be great. So I'm going to go text. Let's, we'll go faster model training with TensorFlow mixed precision. Link. Use less bits during training for faster, but still just as performant model training. And we want CDocs for more. Let's go to mixed precision. What I want to do is a fairly straightforward example. So yesterday we did a whole bunch of massive amount of comparison. And we learned that if we fine tune a model, the more layers that we have, the more mixed precision helps. So mixed precision doesn't really help, we learned, if we're just doing a feature extraction model. But whilst fine tuning, we see a massive improvement. So that's probably what I'll do. I'm going to go text here, build a feature extraction model, and then we want to go fine tune without mixed precision, slow. I'm going to put to do. This is what we're going to do. We're going to write the code for all of these sections today. And this little tutorial notebook. Maybe I'll even turn this into a blog post. That could be a good idea. To do fine tune with mixed precision. Fast. So what do we need to do? We need to build a feature extraction model. We'll probably do a smaller data set than what we did yesterday. Full stack DL, what's up, my man? Can you hear me properly, Ashik? If anyone's in the chat, I always need, when we first start, I need to know if the audio sounds good, because for some reason, it doesn't always tell me. It's coming up as it is. Hasmanado, what's up, my friend? How you going? So today's stream, this is what we'll do. What we've done, build a simple notebook to demonstrate the power of mixed precision training. This can be used as a reference for course materials. Okay, what we're doing today, what we've done. Yeah. So use a smaller data set, faster training, showcase difference between mixed precision training with fine tuning and feature extraction. Wonderful. So mixed precision actually probably works best from scratch as well. So let's do that as well. From scratch. From scratch without mixed precision. Let's do that. Yeah, good idea. Without mixed precision. And Command MB to do from scratch with mixed precision. Okay, so what will we need? We need to get data. To do get data. So we will, how can we get a data set? Import TensorFlow as TF. Let's see how much of we can do this just by purely just guessing what to do. So I've got a bunch of data sets that I've prepared for this. TensorFlow Deep Learning GitHub. Amazing, amazing course, amazing resources. Let's do 10 food classes, 10%. Copy that. Come into here. Import TensorFlow as TF. What else do we need? Import matplotlib. .pyplot. Why is Colab not as PLT not giving me a runtime? We're going to need a GPU. Save. Are we using a GPU? Are we using a GPU? TK, I'll fill in this text later. Mixed precision requires a NVIDIA GPU with a score of over 7.0. And we need, have we got a GPU? NVIDIA SMI. We have a P100. Oh, that may not work. Shit. Note. Colab's P100s Does this? I think this is true too. Colab's P100s might not work with mixed precision. Need T4 or above. This might be a little bee in our bonnet. Import, or no, from TensorFlow.keras. Now we'll set up mixed precision here. No, we'll set it up here. Do you have the right GPU? No, we shouldn't do that actually, because we want to do it without mixed precision first. So let's see here. How can I get my GPU score? Jesus. Audio is good. Thank you so much. So, mixed precision. What methods does mixed precision have? TF-Keras mixed precision. So we need a GPU with a score of over 7. Come on, mate. Give me the documentation. Let's just import from mixed precision. Import mixed precision. Is there a method here from mixed precision that tells us global policy? Is this going to tell us? Is this a method? Policy. It needs a name. You can look up compute capability for your GPU at NVIDIA's CUDA GPU webpage. Examples of GPUs that will benefit most from mixed precision. Oh, here we go. If running this guide in Google Colab GPU has a P100 connected, the P100 has a compute capability of 6.0 and is not expected to show... Damn it! We're running a P100 at the moment. So, can we just reset our runtime and get a different GPU? Restart runtime. Factory reset runtime. I'm going to see what that does. Reconnect. Connected. Now, what type of GPU might we need? Yes, we got a T4. Okay, so that's the trick. If you get a T4, need T4 or above. If you get a P100, try going to runtime, factory reset runtime, and keep resetting until you get T4. Use the command below to see what GPU you're running. If you get a P4, try going to runtime, factory, reset runtime, and keep resetting until you get a T4. Wonderful. So now we have a T4. We do have the right GPU. So what we need to do now is get the data, and then we're going to just build in these cells to build a feature extraction model, to do from scratch. We'll build a convolutional neural network, train it for a few epochs, see how fast the epochs are, get data. Okay, let's do that. wget. And I'm going to import my helper functions because I don't want to just be rewriting code all the time. So extras, helper functions. And wget, get data and helper functions to save a bunch of boilerplate code. And then from helper functions, import, what do we need? I'm not going to reinvent the wheel here. I'm going to go to a previous notebook. So this is where you get to once you've done a fair few experiments. You just start to go to old notebooks and just import previously written code. So here's one of the notebooks I prepared earlier, like a great cooking show does. Should I just get these? Yes, I should. From helper functions, I don't think we need plot loss curves. Do we need that? Nah. And we also don't need compare histories. We need walkthrough, maybe TensorBoard callback. We will delete it, and if we need it, we can import it later. Unzip data and prepare training directories. Unzip data, 10 food classes, 10%. .zip. So, do we want 10 food classes or do we want 100 food classes? Do we actually want a bigger data set, don't we? Because 10 food classes, 10% is only 700 images. So we want a bigger big dog data set. So I'm going to copy this. We don't want the full Food 101 data set because that'll just take too long. But we do want at least something decent, you know? So I'm going to change that to 101 classes. All right. And then how many images are we working with? Walkthrough 101 food classes, 10%. Input, no, unzip data. This should all work. And then prepare train and test directories. So train dir equals 101 food class, 10%. Oh, no, this should be classes. Classes, 10%. So a very important thing in machine learning, of course, is getting a data set ready. So I really recommend, if you want to run some sort of experiments on different types of data sets, I'd prepare some of your own and have them really easily accessible so you can run some boilerplate code like this. I could actually just put this all into like a GitHub gist and then just run this, and then I've got a data set ready to work with. So if I wanted to run an experiment, like a modeling experiment, I've got a data set ready to go. So run. This shouldn't take too long. Now the goal of this stream is to fill out this entire notebook with code. Let's see how much better mixed precision training is than not using it. So we're going to prepare the data set. Prepare data set. So we need train data equals, oh, what did we get wrong here? Hold on. Where is that going wrong? Doc type HTML. What? Okay. So very important point. If you want to download something from GitHub, make sure it's in raw format. Raw. That's the motto of GitHub. keep it raw. And we'll go Control V, run, boom. What's everyone working on? What's exciting you in the world of ML at the moment? Now let's unzip our data, I'll walk through the directory, see how many we have. And we're going to set up the tfkeras dot. Is it pre-processing? Image, data set from directory. We need traindir. And then we need, oh, what is the docstring of this? tfkeras image data set. Yeah, it is pre-processing. What are the parameters of this again? We need image size, that's it. Image size equals 224. And we also need label mode equals categorical. Oh, Ashik, you're too kind, my friend. Prepare data sets into batched data sets. You're too kind. I appreciate that you're enjoying the course. So this is the data set that we're working with. We've got a fairly large data set. This is exciting. Test data and train data and test data. So if we have a look at this, we have 101 different classes with 75 images in each. So what's that? 101 times 75, 7,500 images. Okay, so hopefully we see at least a significant speed up with mixed precision, and then a whole bunch of testing images. But we're more so worried about model training here. TF is not defined, my goodness, as TF. What? Found, okay. Why is that? That just messed up. $32,825 files. That's interesting. What the hell? Batch size. Oh. Did you pick up on that? Okay, that's where we messed up. We forgot the right training paths. Beautiful. Now let's build a model from scratch. What should we use? Should we use TinyVGG? From scratch without mixed precision. So let's go build a model. No, rewrite it. Let's create a function to build a model. Create a model. So def create TinyVGG. So I think for mixed precision, we can just set up a simple bool. Nah, actually, we'll just code this from scratch. So, TinyVGG. This is what powers CNN Explainer. we'll just code up this model in TensorFlow. Can't really see it. Come on, is this site gonna reload? Yeah. Column value, max pool, column value, max pool. Okay. Nice and simple. And we'll do that. So let's go inputs equals, we'll actually get layers, by the way. So code from TensorFlow.keras import layers. So import is layers dot input shape. We'll set input shape as a hard-coded variable, global variable. Just a simple 2243. Of course, you could change that to whatever you want. Inputs, and then we'll go X is going to be, do we need a flatten layer? I think we do, we don't? No, I think convolutions can take conv2D. And then what are the filter size? So what's conv2D? Filters equals 3, kernel size equals 10, strides equals 1, and then padding equals valid. Activation equals relu. And then X equals layers. Oh, actually, we need to pass inputs. And then X equals just the same again. conv2D, 3, 10, 1. We'll just set 3 and 10 actually, because you don't need, all the defaults will work. And then that'll take X, and then we have X equals layers. Max pool 2D. You can set the default there. And then we need the same again. So we're just stacking a bunch of layers. And then the output of that equals layers dot flatten. Because we need to pass it into a vector. We need a feature vector for the outputs. Outputs equals layers. We're gonna, by the way, this model probably won't get very good results on the problem that we have. But we'll beat it with convolution, with a transfer learning model later. Model 1. And clean this up later. I just want to write the code today and we'll clean this up later. Beautiful. If you're joining the stream, we're playing around with mixed precision training. Whoa. Will you upload the old Twitch videos in YouTube or in Twitch again? Simply Samarth. I'm not sure. I think I'm just going to do these as live streams, and if they get deleted, they get deleted. If enough people want to see them on Twitch again or YouTube or something, we can consider re-uploading them. French Toastmaster 97, hello from New York. I'm working on a Kaggle dataset to predict credit card approval now. I also have every intention of doing the new course after. Looking forward to it. Oh, thank you, my friend. Wish you all the best with your project, and the course will be waiting for you when you are ready. So this mic, I don't think is heavy enough to stay here. I've got my other mic, my better mic, is in my recording studio. Can I just leave this? Come on, stay. Can you hear me if I just sit it there? If the mic flings off, I might just leave it there. tfcarers.model, inputs, outputs. So this is on boilerplate model code. Compile model. Now model 1 equals model 1 dot, oh no, we don't need that. Model.compile, and then we're going to set up the loss equals, did my keyboard just die? Wow. Nope, we're back. Equals categorical cross entropy. How quickly do you think we can get this notebook done? Because I have somewhere to be in about an hour and 15 minutes. So I'm cooking dinner tonight for my family. I'm very excited. You know what? We could build a model in this notebook to recognize what I'm going to cook for dinner. How's that sound? The test image of the models that we're building is what I'll cook for dinner. And then we want metrics equals accuracy. I want to do more Twitch live streams, so because I want to show you what it's like to really actually work on a problem rather than sort of just make highlight videos on YouTube. I think Twitch live streams go through the whole thing. Of course, you could cut some things out and make it highlight for YouTube, but I want you to, plus it helps me practice my thought process and explaining different things. And now we're going to fit model. This is taught in the TensorFlow course, by the way. 1, create model. 2, compile model. 3, fit model. Nice and simple. We'll go model 1. No, we want history variable. History model 1 equals model 1.fit. We've got some train data. We're just going to keep it simple, nice and 5 epochs. We will go validation data is our test data, which is already pre-formatted, thank you. But we're going to do a little less validation steps. Is we're going to do 15. Oh, actually, let's create this. Val steps equals int len int 0.15 times len test data. Only step through 15% of test data during training. Faster. Save us recoding that, val steps. And I think we should be off to the races with this. Do you think our model's going to work? Tiny VGG. C here. CNN explainer. Done. All right, are we ready to fit? Let's try. If in doubt, run the code. Oh, what did I get wrong? Input has no variable shape. It's just input shape. What did I get wrong here? None and 10. Oh, we have 100. See, this is where you should hard code stuff. Num classes equals len train data class names. Get number of classes. This will be our output, our number of output neurons. Is that neurons? How you spell neurons? No, neurons. Wonderful. Num classes. Is that only 3 filters as well? No, I think this needs to be reversed. Filters equals 10, and then the kernel size is 3 by 3. That's much better. 10, 3, 3, 10. Or actually, let's make it a bigger model, you know, because I want to see some... I want training to actually take a decent amount of time. 64, 64, 64. Okay. Let's see if this runs. Num class is not defined. Input image shape. What else have we got wrong? Num classes is not defined. Num classes. Num classes. We're on. Fish on. Great idea with Twitch. Gives an expression what it's like to do ML. Thank you, Shvans. I really appreciate it. Ashik, thank you for the comment as well. Because I want to, like a Twitch live stream, right? I could, oh, look at this. Our model's training. Okay, so right now, this is what we're paying attention to. It's taking about a minute per epoch. Is it learning anything? Oh, do we might need to normalize our data? I don't think it's normalized. So, okay, this is why our model's not training. So we can do this by x equals layers dot pre-processing, or layers dot experimental dot pre-processing dot rescaling, and the scale is 1 divided by 255. Watch this. I reckon our model's going to train now. Scale inputs required or your model won't learn. So I think this is going to work now. So look, this is after 30 seconds of training or 40 seconds. So look, okay, this is how we can quickly deduce this. What is happening here? Colab, I just want to make another cell. So results without scaling. I actually want to like stream the entire, after the course is finished, that's what I'm working on at the moment, finishing the course. I actually want to stream the entire building of my next project. Like just start from scratch and just build the whole thing live, and then maybe make some highlight videos on YouTube, so they could be like 10 minutes long of like progress updates, but then we could just build the whole thing live on Twitch. I think that'd be really fun. Watch. Will our model learn now? Maybe we just had to wait. Or maybe our model's not powerful enough to learn. This is live model diagnosis. You can't get this content anywhere. See, our model's accuracy is stuck. Loss is going down, but Christopher, what's going on, brother? I'm not using Colab Pro. I'm in Australia. Colab Pro is only available in the US. So Colab Pro, I probably would sign up to it if it was available in Australia, just because I use Colab almost every day. And I mean, $10 a month, I can afford that. So where is it? Where is Colab? Yeah, there we go. Only available in the US and Canada. So I'm in Australia. Maybe I could just use it through a VPN, but I can't be stuffed doing that. Okay, so our model is not learning. How do we diagnose this? right? So let me just show you an example. So we have 101 classes. 101 divided by, or 100 divided by 101. This is the result our model should get if it's guessing. Oh, it's not going to show me that, is it? Because it's got a cell running. 101 divided by 100 equals, okay, so it's going to get times 100. Okay. Play with me here. Okay, so this is our results if our model's going to get if it's guessing. And this is what it's guessing. It's getting right now. So, our model is not learning anything. Why not? Probably because the inputs is something going on there. So, let's have a look at our training data. Train data. What did we do differently in a previous notebook? I don't think we did much different. Categorical, shuffle, yes. Where's our pre-processing? We didn't pre-process, but that was because we were using a trained model. Okay, we need to stop our model here. See, look at that. Okay, everything is working. What if we try SGD optimizer? Oh, okay, I think it could have been Atom. No. Let's stop this. Let's increase the learning rate. Atom, 0.001. Still going. Well, we've rescaled. Relu. What is the input shape for Con2D? See, I hate this with Colab, is while something's running, it basically can't do anything else. There we go. Let's inspect our training data. That's a better idea. Batch data set, yes, that's what we want. TF float 32, okay, beautiful. And then we want, what can we do? Train data next. Dot take one, and for images, labels in print images, I only want one image and one label. Okay, so our images are getting read in as floats. Now if we want to times 1 divided by 255. I think I found maybe what the issue is. 1 dot. Okay. I think our rescaling was wrong. That's why we need to move the decimal over here. Intuitively, that doesn't really make sense, but let's see if it works. Still not learning. Activation Relu. Activation softmax. Loss is going down. Let's stop that there. Um, how's the next Machine Learning Monthly going? It's going great. The article version is out. You can go Machine Learning Monthly. The article version is out for February 2021. Just can this, or just go to ML Monthly tag. ML Monthly, boom. February 2021. If you want that, I still need to make the video version. So that'll be out soon. So, Hands-on ML is a phenomenal book. I have that right here. Check that out. Hands-on Machine Learning. I have a lot of bookmarks, as you can see. This is still like the ground truth for a lot of machine learning right now. But my course is basically a video version of the TensorFlow part of this. That's how you could describe it. Why is our model not learning here? Is it not powerful enough? It should be. Like, it's getting worse than guessing. Maybe it's too convoluted. Oh. Nope. Still performing poorly. I don't get this. What have I done wrong? 03. This is why it's helpful to have notebooks at work. Maybe I've got too little filters. Multi-class. Maybe we've got too many filters, actually. I think that's what's happening. Too many filters. Hey! Okay. So the model was too complex. If in doubt, I made it too complex. There's a mistake. Make your baseline simple. So this should work now. And maybe I just wasn't being patient enough for it to learn. Adam, is the LR? The LR is default. Whenever you run something on Colab, you can't check anything else. Yeah, Siobhan's, I highly recommend, you could just read the book and do the exercises without doing the course. But if you like to hear things and have me code along with you, you can do the course as well as the book. So I will never say like my course is better than anything else, because let's be frankly, like, everyone's going to learn differently. Some people like to learn watching videos. Some people like to learn watching books. I myself prefer to learn watching a whole bunch of things. You can learn all of TensorFlow without even the book or without the course in general. You can just go through the documentation and read through it all. But if you want, in the course, we basically write all of this code together and we build projects, things that I've worked on for many hours. Okay, here we go. Oh, but the validation accuracy is just absolute mud. That's all right. We're only looking for model training time with this. So the training accuracy is actually pretty darn good for our model. Needs some What happens if the training accuracy is way above the validation accuracy? What do we do? What's our model doing? Now, how do we turn back to just what are the types of policies? How do we turn mixed precision off? There we go. Beautiful. So we can turn mixed precision on. Turn on mixed precision. We need to So here's where the Model 2 is going to come into play. We're going to use the exact same model as before. So look at this. Performed pretty poorly in validation accuracy, but that's okay. It got great training accuracy far out. So our model's not generalizing well. It's taking around 40 seconds per epoch, 37. So let's see if mixed precision speeds that up. So mixed float 16. Here we go. So note, this requires a GPU with a compute score of 7.0. P100 won't work. Colab P100s won't work. Okay, beautiful. So now we can turn this into Model 2. Model 2. But we need to change one thing. Create a model to use mixed precision training. Things to note. Model is same as above, except for output layer. Output layer turns outputs back into TF float 32 data type, more numerically stable. Boom. So Note, output layer of mixed precision models should be D-type equals float 32, more numerically stable. So we can do this by separating the activation, dense num classes. I need to TK this to look at it later. Dense number of classes X, and then we will change the outputs to layers.activation. Softmax. And we'll go D-type equals TF float 32. And we can go name equals output activation. Or softmax. Softmax activation. So does that make sense? All we're doing is we're changing the output layer to do D-type float 32. Because if we go down here, yeah, can computationally override layer to use float 32 instead of mixed precision. So that is because in the guide it says that the output layer needs to be incorrect. Softmax and model will output float 16 when it should be float 32. And we have here, correct, softmax and model output are float 32. Wonderful. Do we put X on the end there? No, we didn't. We forgot X. X. Okay, so once we run this cell, if mixed precision does speed up our code, we should notice a drop in the epoch time. So right now it's 37 seconds per epoch. I need to go take a piss because I've been drinking a lot of orange juice and coffee. So you watch this and tell me if our epoch time has gone down. What? We can't have a space. Boom. Whoa, whoa, whoa. Maybe it would be good to start with fewer layers and neurons and add up. Yep, you're right. Overfitting, definitely overfitting. How do you handle creating your own metrics to measure your models? Really depends on, it's whatever you need. So what's the business metric that you're trying to optimize? Oh my goodness, mixed precision is taking longer with this. This is interesting. Wow. So maybe with smaller models, it's not as good. Very interesting. We have the exact same Everything's model 2. Model 2. That is very strange. Yeah, I think it should be with. I needed to sneeze. My bad. Wow. Okay. It could be because the convolutional layers are pretty efficient as it is, so we're not really seeing much of a speed up. So we'll keep going with our test. I want to see what it looks like with fine tuning with a bigger network, because really this is a toy network, right? So it's performing absolutely crap on our data. So we wouldn't even use this toy network. So let's keep going and we'll build a feature extraction model. First, we'll turn mixed precision off. Mike, please just stay. Oh my goodness. If I have my mic up here, can you still hear me? Because I can't be stuffed moving it. Mixed precision dot set global policy. What is the policy for mixed precision off? Policy. Can you still hear me if my mic's just there? Float 32. Okay. So that sounds better if the mic's there. Thank you, Ashik. Thank you, everyone. Guys, if you're wondering, if you just joined and what we're doing, we're building a simple notebook to demonstrate the power of mixed precision training, but we've just kind of worked out that it might not be very good for small models. In fact, it's slightly more, it takes a few seconds more on a small model. But how often are you using those actual models in production, right? So now let's build a feature extraction model. We're going to use EfficientNet B0. So create a feature extraction model. So we want base model equals TF carers applications EfficientNet B0. We don't want the top because we're going to add our own top. False. And we just turned off mix precision, so it's off. Reset back to default float 32 data type. And we need more code here to do later on. So turn on mixed precision. Now I have to be somewhere in about half an hour, so I wonder if we can get all of this done. We sure can, of course we can. Base model dot trainable equals false. I only have to really write this once, because then we can just copy and paste it later. And then we want inputs equals layers dot input shape can be input shape, which is our global variable, and then x can be base model inputs, and then we'll set training equal to false here. Training equals false. Got an itchy nose. X equals layers global average pool 2D. And we want to take X on the outside. And then we want X equals layers dense. Did I need that flatten layer there before? Yeah, I did. Global average pool, input base model dense, global average pool equals num classes. Activation can be soft max and X. And I know that can just be our output layer. Outputs. Very simple fine-tuning model. See, so this is a pre-trained model, and then this is our dense model, but every layer in the fine-tuning in the pre-trained model is going to be frozen, and we're only going to train this final layer here. But this is model 3 equals tfkerras.model inputs, outputs, and then we want to come back up here. Compile the model. Compile and training code is actually boilerplate too. And when I say boilerplate just means like you've written the same code before. So you'll hear a lot of this jargon when you learn to code and whatnot. I don't know all of it. I probably say a lot of jargony things because I've been coding for a while now. I'm acting like I'm some sort of programming expert. I'm not. I'm still learning all of this stuff well and truly. But jargon or boilerplate, I learned the other day, is just code that you've written before. So why would we reinvent the wheel? Okay, feature extraction model. So this should perform way better than any of our previous models because it's pre-trained. So here's what our hard-coded model ended up as, with more lines of code than our pre-trained model. We got 3% accuracy on 100 classes, which is slightly better than guessing. Let's see how our pre-trained model goes. Oh, you know what we need? We should have checkpointed this. We'll see how long this takes anyway. Yeah, it doesn't take long. Create a model checkpoint to... do we actually need that? No. Build a feature extraction model. You're right. With mixed precision turned off. So model 3 is feature extraction turned off, with mixed precision turned off. Model 4 can be feature extraction. This is the experiments we're running, with mixed precision turned on. And then we want to copy this cell. We'll see if mixed precision helps with feature extraction. I doubt it will much because it's only going to help with one layer. Where I think it will help the most is with fine tuning. Turn on mixed precision and then fine tune without mixed precision. So I'm going to put this up here. Okay, boom. This is a great experiment, isn't it? 9 Lich says, hey Daniel. What's going on, 9 Lich? We are learning about mixed precision, which is a very cool feature of TensorFlow that got added in TensorFlow 2.4. TensorFlow 2.4 is very new. But I want to include this in the course, so that's why we're working it out. What version of TensorFlow is Colab running? Import. Print. TF version. No, we need the dot there. Version. Hey, waiting for it on Udemy. It should be there soon. And the bonus thing for Udemy, by the end of the month, it should be on Udemy. The bonus part with Udemy is there should be at least another, I think I've recorded 180 videos at my last check. So when it's on Udemy, there should be at least like 220 maybe. So where's my video count? All this stuff will be in GitHub at the moment. Launched. Yeah, so 182 videos so far. There'll probably be close to 220 on Udemy by the time it launches, of pure TensorFlow goodness. I'm working out some new features for it at the moment. Okay, so the feature extraction model takes about 45 seconds per epoch. Okay, so this is going to be a bottleneck for us. right now. So we need to set layers in base model to trainable. So what do we want to do? No, we'll check the layers to see if they're trainable first. Check to see if base model layers are trainable. For layer in model 3 dot layers, we want, okay, so our fine tuning took about 45 seconds per epoch. Let's fine tune without mixed precision. Only for about 3 epochs though, because we don't have all the time in the world for this session. Layers, no, it's going to be first layer dot layers, print layer dot name, and layer dot trainable. So right now, all of the layers are frozen. So you see here, layers in our base model, are they trainable? False. So if we want to set the layers in the base model to trainable, for layer in model 3 dot layers 1 dot layers layer dot trainable equals true. And then print layer dot name layer dot trainable. True, 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 true. Are all the layers in the base model trainable? For layer in model 3 dot layers 1 dot layers, we want print layer name layer dot trainable. True, 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 true. So we just set all the layers to trainable. So now we want to fine tune without mixed precision. All base layers are now trainable. So we can just go history model 3 fine tune equals model 3. Let's train for another epoch. How many epochs should we train again for? Train data epochs equals 3, and then validation data equals test data, and validation steps equals val steps. So this is without mixed precision. Oh, this might take a fairly long time. Oh, there we go. By the way, this is how well our feature extraction model performed. 60% accuracy versus 3% accuracy of the model we built ourselves. So power of transfer learning, HALA, transfer learning is a beast. Oh, wow. Why is fine tuning so quickly? Why did feature extraction take longer than fine tuning? What? True, 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 true. I'm perplexed here. Oh well. Pretty good training accuracy. And we're getting a slight increase. So fine tuning takes 46 seconds per epoch without mixed precision. Hopefully that automatically recognized the fact that I reset float 32. So this will be interesting as well. Create a model compatible with mixed precision training. Wonderful. So that actually didn't take too long to fine tune. And we didn't get a dramatic increase in results, but that's okay. So I think where mixed precision is going to help the most will be with when you have a really large amount of parameters. So that probably makes sense too. Is if you don't have a really large amount of parameters, it's going to be fairly efficient to compute anyway. Compatible? Is that how you spell compatible? Compatible. How do you spell compatible? No. Compatible. Ible. It's compatible. Compatible. Now we need to note for mixed precision, output layer should have D type of float 32. Okay, so here's how we can go x equals layers.dense num classes. That's going to take x, and then this needs to change to activation, and this can be soft max, and this can be D type equals TF float 32, and then name equals softmax. And that takes x. And this is model 4, isn't it? Model 4. History, model 4, and model 4. So we'll turn on mixed precision. That didn't output anything. To do, check what compute D type is. Verify mixed precision is turned on. So, how do they do that in the documentation? There we go. I prefer F strings than percentages, so let's do this. Policy compute D type. Oh, they save it to a variable here. How do I get the current policy? Global policy. Okay, there we go. Check the make sure it's global policy dot. Does this help? Wonderful. Haha. There we go. Print. If in doubt, visualize, visualize, visualize. So this should be mixed precision. Feature extraction. We should get very similar results to what we got up here. It may even be slightly faster. So I want to do should output. How long did that take us? 46 seconds. Oh! Yes! There we go. Look at that, Twitchies. Twitch team. I'm going to hide all these outputs because there's way too many. But look at the time per epoch at this. The loading epoch took the longest. Did this one take less time? Hold. Maybe it didn't because it needs to verify. Okay, 46 seconds, but that's still over 10% quicker. Oh no. No. Here. 45 seconds. So we've got a reduction per epoch of 10 seconds for feature extraction. Now that's actually very good. 5 seconds, sorry. But 5 seconds is just over 10% of 45. Oh, it's consistent. That's what's up. That is cool. So we're getting verifiable 5-second improvement per epoch. Now, are we getting the same result? We can check this by going now, it might not seem like much, but this will add up over time. This is amazing. So you imagine 10% over the lifetime of all the models that you build. You just saved yourself 10% of your time. Albeit this is a small experiment. This will be a really cool one to see how it goes with make all layers in base model trainable. Verify all layers in base model are trainable. For layers in model layers 1 layers. No, this needs to be model 4. Compare results of model 3 and model 4. No, we can't do that yet, can we? Because model 3 has been fine-tuned. So these actually need to go down here. But we just saved 5 seconds per epoch. Be very interesting to see here. Layers No, for layer. Layer dot trainable equals true. For layer in model 4 layers. 1. Are all the layers trainable? Dot layers and print layer dot name layer dot trainable. All the layers are true. Now we will fine tune model 4 for 3 epochs with mixed precision turned on. So what did we do for model 3? Boom, we'll just copy that. With mixed precision, all base layers of model 4. Model 4. Model 4. Moment of truth. Oh, that looks like it might be quicker. I hope so. I think, yeah, this will really improve if you have more data and more... You know what? I think it might even be our data loaders aren't as efficient. So we could probably really step this up. Does it say anything about data? Yeah. Okay. You should run input processing math in Float32. It runs on the CPU. Where's our data getting loaded? The first layer of the model will cast the inputs to Float16. Maybe that's what we need to do. Oh no, it does it automatically. Yeah. Where do they create their model? They do it in that strange fashion. What do we get here? How's our fine tuning going? We don't see much of a difference. 40 seconds. How do they both perform? So fine tuning, we save about as much as we saved before. We do save some time though. Eagle eye observation, baby. Well, it did say up to 3x performance. Oh, on CPUs, mixed precision will run significantly slower. Huh. You know what? I think we'd see the biggest accelerant if our data loader was better. Does this have a prefetch option? Image data set from directory. Batch size 250. Maybe can we speed up data? Data loaders? Train data equals train data dot prefetch TF data auto tune. Test data equals test data prefetch TF data auto tune. We did this before because the main bottleneck, they said mixed precision will be faster on a GPU. So potentially our bottleneck is when our data is loading on the CPU. So we're missing our speed up time, prefetch. Prefetch, TF data auto tune. Oh, this might be the money shot. So yeah, they get basically the same result. Oh, but there we go. Inference is 10 seconds quicker. Basically the same result. See here, mixed precision, non-mixed precision. I mean, sorry, wrong way around. Non-mixed precision. And this is, how long have we been going for? An hour and a half? Oh, don't want to do that. Mixed precision. Without prefetched data. Oh, this might be an absolute game changer if this works. So we go down here. Mixed precision, fine tune, results without prefetched data. Control V, Control A, boom. We go here. I think if we could speed up our data loaders, would we? Obviously we would. So mixed precision without prefetched data. I think we might have a little insight here. And this is because all of your bottleneck will be loading data from the CPU to the GPU. All right, here, mixed precision with without prefetched data feature extraction. But we also then might get an additional speed up for, I don't know if this is possible. This is just an experiment, right? I don't know if this is going to work. Do not know. Absolutely do not know. By prefetching. Batch data set has no attribute prefetch. Oh no, it's because I spelt it wrong. Oh my goodness. We might actually be able to speed up our data. Prefetch batch data set. Ho! Okay, let's retrain our feature extraction model with prefetched data. This may be the kicker. Where is it? Build a feature extraction model with mixed precision turned on. Are you ready? Are you absolutely ready? I just want to make sure mixed precision is turned on because we might have just sped up our data loaders something fierce. You're seeing this live. You are seeing this live. Okay, pay attention to the epoch time that we got here. All the difference that we made here was prefetching data. Data. Does it mention prefetch here? No. Where does it say data? Do they prefetch? They don't prefetch. TF dataset from TensorSlice's shuffle batch. Maybe it's already fast enough. Well, you know what the motto is. If in doubt, run the code. We've now prefetched our data. Fingers crossed. The first epoch might be a little slow. Oh, did we get a speed up? I think we might have got a speed up here. The first epoch might be a little slower. Look at this, team. Look at this. Are we going to get faster data? I got to cook dinner tonight. What should I cook? Are we going to get a speed up? 46 seconds. Time to beat. Look at that. Look at that. Look at that. Ladies and gentlemen, data loading of the gods. 34 seconds. Improvement on 46. Look how much faster we've just made our data loaders. 28 seconds. Holler at your boy. You just doubled your speed, your epoch speed. Doubled it. Halved it. No, not doubled it. Halved your epoch speed. With mixed precision and with prefetching data. That is what's up. Just saved yourself 50% of time. You don't understand how good that is. If in doubt, run experiments like a madman. You just saw that happen live. How do we record this shit? I wonder what it's going to do for fine tuning, right? Fine tuning took us 40 seconds per epoch last time. What are we going down to? See, this is the stuff you don't get from the documentation. Documentation, scattered all over the place. Experimentation, works. Look at that. Without prefetched data, 46 seconds for the first epoch. With prefetched data, 40, no. So we saved 12 seconds per epoch. What is that? 40 divided by 12. A third. We saved a third. 12 times 100. No, how do you get this? Oh no, it's 12 divided by 40. How do you get percentages? It's about a third. I never remember the formula for percentages. They taught it in year 10 and I can't remember it. Look at that. Same results. Same results. 30% faster. All right. Now, we don't need that. This is prefetched data. So, this is just two simple tricks to speed up your code to go, look at this. We went from without prefetched data, we went from 45 seconds per epoch, and then we turned on mixed precision and we prefetched our data, and we got 28 seconds per epoch. There are probably some more optimization steps that we could have, but how good is that? So now we got mixed precision with prefetched data feature extraction. So stuff mixed precision, actually, you can prefetch your data. That's what's up. So I think this is actually documented. Prefetch, TensorFlow, prefetch data. This is the stuff you don't get. Oh, better performance with the TensorFlow. Here we go. Maybe you do get that. I'm going to save this for later. ML. And then prefetch. Prefetching overlaps the pre-processing and the model execution of the training step. Boom, there we go. Execution time. Yeah, see you see this stuff? Open, read, prefetched. So it all overlaps. Massive plays, massive plays. Okay, I'll read up about that later. This is advanced TensorFlow shit right here. Well, not really. You should really work out how to improve your data set. So if you're doing the course, start adding, this is going to be in the extensions section, so don't worry. If you're doing the course and you're using batch data sets, so using this method, add prefetch, add this, Ashik, to all of your code. Train data.prefetch tf-data auto-tune. And you should get prefetch batch data set, should load faster. Just work that out. Now let's fine tune with prefetch data. So we've done feature extraction, we want to fine tune. True, true. Are they trainable? And we want to check mixed precision global policy. Yep, we are on. Now, noticed here, this is before, without prefetched data. So 40 seconds per epoch. Same, all we did was prefetch our data. Now, what are we going to get for this? Oh my God. What the hell? Yep, Ashik, prefetching the data has made this improvement. And what does prefetch data means? Hey, Toma, greetings, Redbird. What's going on? So this model, we're doing, it predicts on different food images, but right now we're just working with different optimization techniques to train our models faster. The number of elements to prefetch should be equal to the number of batches. So I don't actually know what prefetch, so TF data auto-tune is going to prefetch as much as possible. So basically what it's saying, Ashik, how I understand prefetching is you have a data batch and you have the data exists on a CPU, and as the GPU is training, it's like, give me a data batch. But if you don't do prefetch, it'll just wait to go CPU, batch, GPU, and it'll process that, and it's like, okay, then give me another one. And then it has to shift a whole data batch to the GPU. But if you turn prefetch on, it sets it up so that the CPU gets the data ready of another batch, almost like basically as the first one's done. So it's just a constant, the train works a lot better. That's what prefetching does. Whereas if prefetching is not turned on, the data loading from CPU to GPU takes longer. So I think prefetch will actually improve all of our models' results, all of our epoch time versus mixed precision. So the combination of mixed precision and prefetching is what is really going to be our game changer. So let's go, look at that. We save 12 seconds per epoch by turning prefetching on. I think that might be almost universal. Let's see how long evaluate takes. So this one took 99 seconds to evaluate on test data. So non-mixed precision evaluating. So mixed precision actually, hold on, the key point we also missed out there, mixed precision works best when your data is on a GPU. So it actually doesn't help when it's on a CPU. So that's from the documentation. Mixed precision only helps your model when it's on a GPU. So that's why we want to move our data from CPU to GPU as quickly as possible. So this is non-mixed precision, model 3, still the same. And this is mixed precision without prefetched data. And now we want with prefetched data. Is that making sense, what we're talking about here? I keep typing prefetched wrong. So the accuracy is here. About 60% on 101 different classes. And the model is over here. That's our model. Actually, we've got 4 different models. We got from scratch. I might put in titles here. This is model 1. And then this is model 2. Can I make this max? And then this is model 3. Very cool, very, very cool experiment we just ran. Ho ho! We got a massive improvement, a 30-second improvement with prefetch data. So, non-mixed precision evaluation. So prefetch data actually gives us a speed up across the board with prefetched data. And then let's see how fast this goes. So I think our data prefetch might have just given us the biggest speed up of the whole notebook. I want to retrain. Make sure mixed precision is turned off. So mixed precision set global policy float 32, and then mixed precision global should output float 32. Wow. So our mixed precision model is still slightly faster, but prefetching data gives us explosive results. Look at that. Without prefetched data, 99 seconds to evaluate. With prefetched data, 68 seconds. I'm going to start prefetching everywhere. Prefetching and mixed precision. So let's try one more experiment. So this is how long our model from scratch that learned basically nothing, learned shit all. So we want here model 1 from scratch without mixed precision and prefetched data. And then this is model 1 from scratch without mixed precision and with prefetched data. So you ready? What do you reckon is going to happen? 30 seconds, 7 seconds per epoch. The only difference between these two models we're about to train is we haven't used this. Yes, we can. Oh my God. Look at this. Are you seeing what's happening right now? What we just learned. We just saved ourselves a bunch of time. Global policy should output mixed. So we saved ourselves about 10 seconds per epoch on that, just by prefetching data. Again, prefetching moves data from the CPU to the GPU as fast as possible. That's where our bottleneck is. Yep, we'll do NLP in the future, we sure will. Right now we're working on data loaders because that's probably one of the most important things, because that's going to be related to any project. I'm in love with prefetching. You are right, Ashik. And then let's see what happens here. Code. Mixed precision. So Model 2 mixed precision without prefetching. Model 2, now we've got prefetching turned on. Mixed precision with prefetching. So if ever you've got a TensorFlow dataset, use prefetch. Use this line of code will save you almost 30% of your model training time. So take a screenshot of that. If you've got data loaders like this in batch data sets, use .prefetch. Prefetch dataset. So it'll go from a batch dataset using, say, this method, and then you can prefetch it, and then it'll go to a prefetch dataset. And then you will see a speed up of like 30%. Depending on what hardware you're using, of course. This is in Colab. So that's a caveat there. But if you're using Colab and you want a 30% speed up, use prefetch. Now let's do one last experiment before I have to go. So this is mixed precision without prefetching on our model from scratch. Does it change much when we prefetch? Of course it does. It works incredibly fast. And why not do the same with fine tuning? Model 3 without prefetching. Model 3 with prefetching. Dataset dot prefetch. Saving 10 seconds per epoch again. 11 seconds per epoch. How powerful is this? This is so exciting. This is one of the best things I've learned in TensorFlow for a long time. Did I miss this in the book? The data API. Yeah, it hasn't got prefetch here. This is what's up. Okay, prefetch here. Ah, it was an experimental feature when the book was written. This is outstanding. Oh, do we have an option to even improve our data loaders further? I love learning new things. So obviously we're going to run. Oh, I need to go. But not in the name of experiments. Image data set from directory. Do we have an option in here to parallelize this? We don't. That is okay. tfdata.dataset. Better performance with the tfdata API. Prefetching. Wonderful. Parallelizing data extraction. Parallelizing data transformation. Oh. Non-parallel calls. This is outstanding. This is very, very... This is probably going to be an extension. Ah, here we go. Best practice. Use a summary of the best practices for designing performant TensorFlow input pipelines. Use the cache transformation to cache data in memory during the first epoch. Oh my god. Did we just land on another one? Cache. Does this say cache? Oh. We got one more thing to try. Oh, and of course fine-tune feature extraction rocks it. How much RAM does this bad boy offer? 12 gig of RAM. So I'm going to try one more experiment. I think this may... I'll go here, cache the data. We'll go back to our first model. Oh, has no attribute class names. That's all right. to do fix. Let's see if this works. Oh, did you see that? The RAM just went up. The RAM just went up by 4 gigs. Oh my goodness. Look at this. Look at that. Look at that, team. Look at that. Holy crap. The RAM just got jacked up from 2 gigabytes to 7 gigabytes. Oh my god. Look how much time we just saved per epoch. I think this will only work if you have enough RAM. We just went from 40 seconds per epoch to 16 seconds per epoch. Yes, this is the hands-on machine learning book. Very good book. Highly recommend. But you have to write code as well as read the book. Look at that. Look at that, ladies and gentlemen. The first epoch took the longest, but it absolutely busted through. We just went from 30 seconds, 37 seconds per epoch to 16 seconds per epoch. Less than half. Okay, we need to try one more. Float 32. Let's do our feature extraction model. So notice our RAM saving here. Can you see that? You can't see that. So the current RAM, I'll write it down so you can see it. Oh my goodness, that got so big. Okay. Before we run the cell below, I need to really leave because otherwise the food shop's going to be closed and I need to buy dinner for the family tonight. So the current RAM is 7.96 gigabytes. Is it enough to cache data? All right, we ready? So we just took a speed up. So look at our previous speed up with prefetch. It's all about the data loading. Model 3 with prefetching and data caching. It is all about the data loading. Say to yourself, it is all about the data loading. So this is the time to beat. 36 seconds per epoch and then about 30 seconds per epoch after. We started with 51 seconds per epoch. Now you ready? Hopefully we have enough RAM to cache the data. It should already be cached though because we're using the same data set as before. We want to make sure we're not using mixed precision. That is good. Let's try feature extraction with cache data. See what happens. Watch the RAM. 7.96 gigabytes. It's just gone up a little. Oh my golly gosh. 7.99 gigabytes. We haven't changed very much. Eight gigabytes. So what did we start at? We remind ourselves, 7.96. It's only gone up by 0.05 of a gigabyte. 30 seconds. Okay, so we don't see that dramatic of an improvement after caching. I think we might for the second epoch. So if you have enough RAM, caching will dramatically improve your results. Wow. Okay. So this is really good to know. So if you want this, go to the best practice summary. What's interleave? The default arguments of the TF data transformation make it interleave single samples from 2 data sets. Ah, I see. Look at that. We save another 5 seconds per epoch with cache data. That's too big for me. We just did a bunch of experiments, boys and girls. What we're doing today: speeding up our models. Model training with data prefetching, data caching, and mixed precision training. So this is dot prefetch and prefetch, and this is dot cache. Oh my goodness. We learned a whole bunch of stuff this stream. I need to formalize everything that's here and make it readable. Right now it's kind of all over the place. So maybe I need another notebook that explores mixed precision, prefetching, caching. We should just really spend a whole stream just seeing how fast we can get our data loaders. That's what we should spend a whole stream doing. Who's in for that? So I will probably be back tomorrow maybe. We'll do another stream. Let me know if you want to see anything in particular, but otherwise we're going to be optimizing our TensorFlow code to load better models, because that's what I'm doing after all, is building out the course. I may need to add an extension here because I've just realized how much we can speed up our model training by prefetching and caching. So Sheik, give this a go if you're working through the course right now. Try to add prefetch to any batch data set, and then if you have added prefetch and it works, add cache. So if you're going through the course, any model that we build, if the data set's in a batch data set form, use prefetch, and if it's in a prefetch data set form, use cache. So that's going to be the end of the stream. Yes. Yeah, 9 Lich, you're completely right. Prefetch and cache, 2 thumbs up from me. And any plans on a live on NLP in the future? Yes, of course, we will have a live on NLP at some point. I plan to do more live streams, so just let me know if you want to see any live streams in the future. Let me know how I can improve my live streams, because otherwise I'm just going to sit here and write code. So please let me know. You know how to contact me. You can find me online. Search my name and you'll find me. But anyway, peace out, everyone. Thank you so much for joining into the stream. I've got to go get dinner for the family, and I will probably see you tomorrow. So yeah, subscribe to the Twitch, follow it. That way you'll get notified when I go live next. Peace.